Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12th Maths Continuity and Differentiability Part 1. Before we start, we request you to subscribe, like and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin the lesson. So let us start with continuity. So what is continuity? So a function is continuous at a point if the graph of the function has no break at that point. This is the main definition. So a function is continuous at a point if the graph of the function has no break at that point. So again repeating, a function is continuous at a point if the graph of a function has no break at that point. Now let us see the continuity test. So before going to the continuity test, let us take a small example to explain, to understand the continuity. Okay, consider the function f defined by fx is equal to x, where x is greater than equal to 0 and less than 1, and fx is equal to 3 when x is greater than 1. So if we draw the graph, it will come something like this as shown in the figure. Here we can see that the graph breaks at x is equal to 1. So therefore graph breaks at x is equal to 1. We say that f is discontinuous at x is equal to 1. Therefore f is discontinuous at x is equal to 1. Why we say this? Because in this case value of fx at x is equal to 1 is 3. Value of fx at x is equal to 1 is 3. But fx don't approach this value. Do not approach this value. That is, do not approach to 3. Now when x approach 1, then the left hand limit and the right hand limit is 3. Clearly, the graph breaks on left of the point. So you can see the blue lines here. So the graph is broken beyond this point, left side of this point, because fx doesn't approach to 3. So this is the continuity. Now let us see the test of continuity. So a function f is continuous at an interior point x is equal to c of its domain or so the continuity test we can summarize as a function fx is continuous at x is equal to c if and only if it meets the following condition. First, fc exists, that is, c lies in the domain of f. Second, limit x tends to c, that is, fx exists, that is, f has a limit as x tends to c. Third, limit x tends to c, fx is equal to fc. The limiting value is equal to the functional value. These are the three tests for continuity. So, to understand the continuity, let us see few examples. First example, check the continuity of a function given by fx is equal to 3x minus 5 at x is equal to 1. So in this case, function is defined at given point x is equal to 1, and so we can write it as limit x tends to 1 fx is equal to limit x tends to 1 3x minus 5, which is equal to 3 multiplied by 1 minus 5, which is equal to minus 2. Hence, f is continuous at x is equal to 1. At x is equal to 1. So let us see the next example. So the next example is examine whether the function f given by fx is equal to xq is continuous at x is equal to 0. So let us see the solution. The function is defined at a given point x is equal to 0. So we can write limit x tends to 0 fx is equal to limit x tends to 0 xq is equal to 0q is equal to 0. So limit x tends to 0 fx is equal to 0 is equal to f0. Hence f is continuous at x is equal to 0. Let us see the next example. So the next example is discuss the continuity of the function fx is equal to modulus of x minus 1 at x is equal to 1. So the solution is so by definition we can write fx is equal to x minus 1 and where x is greater than or equal to 1 and minus x minus 1 where x is smaller than 1. So why we have written this? Due to the modulus. So inside a mode, whatever the value of the object is which is inside it, either plus or minus, the answer will be in plus. So it can have modulus of x minus 1 can have two values, either x minus 1 or minus x minus 1, plus x minus 1 or minus x minus 1. When plus x minus 1? When x is greater than equal to 1, and when minus x minus 1? When x is smaller than 1. So this is by the definition of the modulus. We can write the function as like this. Okay, the function is defined at 1. So in the question, the function is defined at 1 and f1 is equal to 0. Left hand limit of f is 1. left hand limit of f f at 1 is at 1 and f at 1 is, first let us write, is limit x tends to 1 minus fx is equal to limit x tends to 1 minus x minus 1, and it becomes 0. Similarly, right hand limit of f at 1 is limit x tends to 1 plus fx is equal to limit x tends to 1 plus x minus 1, which is again equal to 0. Therefore, thus the left hand limit right hand limit and the value of the function coincide at x is equal to 1. Hence, the function is continuous at x is equal to 1. Let us see the next example. So, the next example is, so that the function f given by fx is equal to x square plus 5 if x is not equal to 0 is continuous at x is equal to 0, 3 if x is equal to 0. Now, the solution, the function is defined at x is equal to 0 and its value at x is equal to 0 is 3. When x is not equal to 0, the function is given by a polynomial. Therefore, limit x tends to 0 fx is equal to limit x tends to 0 x square plus 5, which is equal to 0 square plus 5, which is equal to 5. Since the limit does not coincide with f0, the function is not continuous at x. Since the limit does not coincide with f0, the function is not continuous. Function is not continuous at x is equal to 0, 0. As well, x is not equal to 0. So no need to write this. Uh, yes, we can just write here that is not continuous at x is equal to 0. We can at most we can write x is equal to 0 is the only point of discontinuity. 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 So the next example is discuss the continuity of the function f defined by fx is equal to 1 upon x minus 1 where x is not equal to 1. So for any real number c, for c is not equal to 1, we have for any real number c for c not equal to 1, we have limit x tends to c fx is equal to limit x tends to c 1 upon x minus 1, which is equal to 1 upon c minus 1. Also, since c is not equal to 1, fc is equal to 1 upon c minus 1. We have limit x tends to c fx is equal to fc, and hence f is continuous at every point in the domain of f. Thus f is continuous function. And this is the end of this today's class. Please subscribe, like, and share our YouTube channel. Please click on the subscribe button to support us, and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos and supporting us. Thank you very much.